Welcome back to Ivy Show, and today we are diving into another AP Calc BC video, and this time it's all about applications of integration. This chapter accounts for roughly 69% of the exam, so mastering all of these concepts is crucial. So let's jump right in. Okay, so let's talk about the average value of a function. So the formula for an average value of a function over the interval a to b is f of c is equal to 1 upon b minus a, the integral of f of x integrated with respect to dx with limits a to b. Right, so let's see how this works with some examples. So in example one, f of x is x squared, and we are integrating from x is equal to 2 to x is equal to 4. So we are going to input all of the values in the formula, and we would get the answer as 28 by 3. Right. Now the second example, f of x is equal to 2 mod x in the interval -1 to 1. So we input all of these values, but we quickly run into a problem. How are we supposed to integrate an absolute value? How are we supposed to integrate mod x? Well, for that, we're going to use a piecewise functions in which we'll basically split the function of mod x into two parts, where if x is greater than 0, the x remains as x, while if x is less than 0, x becomes minus x. So we're going to split the integral from x is less than 0, so -1 to 0 for minus x dot dx, and we're going to add it to the integral for x is greater than 0, that is x dot dx from 0 to 1. Now we'll integrate it as normal and we'll get the answer as 1. Now for our third example, f of x is equal to 4x times cos x square. Here the square is on x and not the function of cosine, and the limits for this are 0 to root pi by 2. Now, you might think you should integrate this by parts, but instead there's a smarter way to do this, and that's by chain rule. So x squared can be written as u, therefore 2x is du by dx, and we can write 4x as 2 times du by dx. Now, inputting all of these values into the function, into the formula, and not changing the limits because you're going to change the entire integrand itself back to a function in x. And solving this, we get the integral to be 2, and we get 1 minus b minus a as root 2 by pi, which is the whole answer is now 2 times root 2 by pi. Okay, so let's now talk about area between curves. So we're gonna take two conditions, vertically and horizontally, and vertically is going to be about x coordinates while horizontally is all about y coordinates. So I have a graph here that is consisting of two equations in x, y is equal to x square and y is equal to x. These two curves intersect and have a region that's bounded by these two curves. That's how we say it in calculus. And we are basically we're going to taking small rectangles with thickness of dx, and we'll be integrating them from x1 to x2, which are going to be the point of intersections and specifically the x coordinates of the point of intersections for both the graphs. And the general formula for this is the integral of f of x minus g of x with respect to dx over the limits a to b. Now, a point to note is that f of x must be above g of x at all points in between the interval of a to b. If for any reason it's not, then we have to split the integral. And we are going to talk about this in detail after talking about horizontal integration. After that, we are going to jump right into this topic. So let's talk about horizontally integrating it. So we are going to be taking small rectangles of again thickness dx, and we will integrate them from y1 to y2, which are the y coordinates of the point of intersections of these graphs. Generally, this is going to be in the form of functions that are in y. So instead of writing y is equal to x square, this should be written as x is equal to root y. And instead of y is equal to x plus 6, it should be x is equal to y minus 6. So your functions should be in the form of y, or you could say it should be x is equal to y something. instead of being y is equal to x something, you should isolate x so that it becomes a function in y. That's how we're going to integrate horizontally. Right, and the formula is here integral of f of y minus g of y with respect to dy with limits c to d. C to d being the y coordinates of the point of intersections of the region of the area bounded by the two curves. Right, and of course it's the same point as the last integral vertically, where f of y must remain to the right of g of y for all points between c to d. So like right here, y minus 6 is to the right of x square in this entire region. So f of x will be y minus 6 and g of y will be root y. Right. Now let's talk about the special case where an function is above another function and then it switches. So here we have two functions in x. We have sine x and cos x. We have two waves, sine y, the sine wave and the cosine y. So as you can see from pi by 4 to pi by 2, sine x is on top, while from 0 to pi by 4, the cos x wave or the cosine wave is above the sine x wave. So to calculate the area, we're going to calculate it vertically. You can also calculate it horizontally using the x coordinates, but we are going to be limiting ourselves to x coordinates in this case. We will be splitting the integral from 0 to 2 pi by 4 and pi by 4 to pi by 2, where 0 to pi by 4 f of x is cos x and g of x is sin x, and from pi by 4 to pi by 2 f of x is sin x and g of x is cos x. We'll integrate this and we'll get our answer. So that's a special case where the functions switch positions and one is now above another. Let's talk about volumes with cross section. So I have a graph here, right, with y is equal to 6 and y is equal to 4 times natural log of 3 minus x. And what we are going to be doing is finding the volume of this area by using some squares or rectangles. And if that sounds a bit confusing, let's step into 3D and let's look at how it would look. So basically, this graph is in 2D and this graph is the same thing but in 3D. So in green we have y is equal to 6 and in pink we have y is equal to 4 times natural log of 3 minus 6. And we have drawn rectangles here which trace the boundary or trace the area bounded by these two curves, and we'll basically calculate the volume of these rectangles. We'll calculate the area of one and then we'll integrate it from limits of whatever we are given, right? We'll integrate it to those limits, we'll integrate the area and we'll find the volume with the cross sections of rectangles or squares. We will find the cross sections with other shapes in the following questions, but let's first do some. Okay, so let's jump right into some examples. So your quadrant one right here is basically, if you draw a graph, you're supposed to travel anti-clockwise. So quadrant one, quadrant two, quadrant three, and quadrant four. So we are basically going to limit ourselves to the area in this quadrant, that is quadrant one. Okay, so now we need to find the volume of a solid whose base is area between this quadrant one and x-axis, of course. And we need to find the cross section using rectangles whose bases lie on the x-axis and their heights are twice their bases. So this is how the graph will look like in 2D, and this is how the graph will look like in 3D. I recommend you to directly draw the graph in 3D, since that would be way more helpful. So the first thing we're going to do is follow a series of steps to calculate the area using cross sections, where the first thing we're going to do is find the integrand itself, find what function we have to integrate. So we are going to be integrating the area, right? That's the entire point of finding volume, of integrating the area. And the area of a rectangle is the product of length times height. In this case, height, because it's a 3D rectangle. So yeah, we are considering the height here. So your height's twice of your base. And the thing is, the value of your base or your length, you could say, will always be equal to y is equal to 20 minus x square. Since to calculate the height at this point, let's say at this point, you need to find the value using the equation y is equal to 20 minus x square. If you were to find the value for a rectangle here, you would still have to use y is equal to 20 minus x square. So to integrate, we would basically write the height or the length actually to be 20 minus x square. That we'll mention as b, and the height is twice that of base, so it's 2b. So we'll multiply the values and we'll get the area as this equation. Now to find the limits, we basically, since we are integrating from x1 to x2, that are two x coordinates, we are going to integrate 0 to whatever this point is, and that is your root. So we're going to be talking about the positive root in this case, since the question has asked us to integrate in for the first quadrant. So your root is root 20. Now, now we have gotten ourselves the limits 0 to root 20, and we have gotten ourselves the equation as well. Now we have to basically solve the integral, which will result in 1908.11 approximately. You can solve the integral yourself, and this is the three steps you have to follow, right? Now let's talk about cross sections with other shapes such as equilateral triangles, semicircles, and isosceles triangles. So the area of an equilateral triangle is given by side square times root 3 by 4. For a semicircle, it's diameter square times pi by 8. And for an isosceles triangle, it's hypotenuse squared by 4. Now let's